Yes, conceptually it's very similar to recursion, but we're not going to do it recursively because we want it to be fast. If you use memorization, yes, you can overcome that, but we're going to do it a little bit differently. Instead of doing it this, I mean, if Ryan is asking Mr. Klages, what's this, what's this, what's this, and what's this, until they get back to this, something that's like here, and then Ryan has no excuse, because Ryan knows that this is 0, and this is 1, and this is 1, so he knows that this is 1, and this is 1, and then he can work out that this is 2. So we might as well, instead of like unwrapping the thing to get back to the top, to get back to the second row, we might as well just start there. Okay? So instead of sort of doing it recursively and sort of unwrapping it, we're just going to start and we're going to do it iteratively. I hope, can I get rid of this now? These rules. Yes, okay. So let's leave this part on. Let's get rid of the rules. I'm not erasing the matrix because the matrix took like not half an hour, but took a while to draw, and we're actually going to need it later. So what we would do would be like, okay, A 0 0 equals 0. A 0 j equals j. So actually that subsumes this, but whatever. A I 0 equals I. This is an I. Can people read this? Okay. So then we say for I equals 1 to, let's say there are m rows, n columns, a 0 to m minus 1, actually we're going to say to m, so there are m plus 1 rows, and 0 to n. Okay, so this is our matrix. For I is 1 to m. For j, 1 to n. Aij equals this, right? Okay, so actually that was a bad place to write. That's the dimensions of my matrix. Aij equals min A I minus 1, j minus 1, plus b. Okay, just this thing. A I minus 1, j plus 1, A I j minus 1 plus 1, where b is b equals 0 if arrow, if diagonal f, okay. I just want this, okay, b equals 0, it's this thing. B equals 0. Okay, so now I can get rid of this. Okay, and so you do this, da da da, and 4, and 4, print AMN. Okay, and that's it, right? That is how you work out the optimal strategy in the matrix path game. Do people see this? This is like not super hard, right? not as hard as like some of the stuff we've done in this class? Yeah, okay, so this is good. So I need to make this harder in order to still beat principles of programming languages. Okay, I'm just going to check that the little camera is, yes, it's recording. Oh, and did I start this? No, I didn't. Ah! So I just have to, uh-oh, I'm gonna reset, and then I'm gonna decrease this to 20. Yeah, start, yes, because I forgot to start. Yeah, okay. Oh, wait, okay. No, but this is actually, okay, I'm sort of kidding around, sort of. Okay, so if I gave you this matrix, you could work out the cost. Now, actually, first, remember I wrote, what is the cheapest path? But then I wrote, what is the cost of the cheapest path? So this actually, I'm just printing the cost, but that's not actually super helpful, because if I just tell you, oh, well, it costs 6, and then you say, okay, how do I get through the matrix? And they're like, oh, I don't know. But it costs you 6, there's some way. Well, you could actually work that out by, when you compute for Aij, right, you could also store at Aij which of these got you, gave you the minimum. Right? So for example, here, when I compute this 1, I could remember that I came, does this blue work? That I got here by coming down this diagonal, right? So I store 1, but if I also store that I got here by this diagonal, and then this 2, I would remember that you probably can't see this at all, but I would remember that I got a 2 here by coming left from a 1. Okay? So for 3, it's like this. And then for 4, I could remember either that I'm coming from the left or that I'm coming diagonally down. Okay, so in fact, if you just store, with each cell, you store how you got there to get the minimum cost, then you can actually, starting from here, you can just follow those blue arrows backwards and recover the actual minimum cost path through the matrix. Okay, you can recover not just the cost, but you can actually recover the minimum cost path. Now, there's a trick that's, this takes, yeah, remember, we're designing an analysis of algorithms. How long does this take? I mean, you have 2 nested for loops, which are going from 1 to m, 1 to m, and 1 to n, so how long does it take? N squared if m and n are the same length. Here, they're not quite the same length, so yes. In general, people say quadratic, it's n squared, but to be perfectly exact, it's OMN. Okay. So yeah, in general, that's n squared. It's the worst it can be when m and n are equal. Okay, so yeah, just if you're only allowed to look at one variable, say n squared. Okay, so that's how much time it takes. How much space does it take? So how much memory? We haven't talked as much about space, a little bit. But generally, the 2 things you want to measure when you're working with algorithms, not always the only 2 things. So you also have, okay, yes, you can in linear space work out the cost. It's not easy to work out I don't know if it's even possible. I haven't thought about that one. since I started preparing this lecture. I don't know if you can work out the actual path in linear space. But to work out the cost at the moment, if we're filling in this whole matrix, you initialize a matrix of A 0 to M and A 0 to N. How big is this matrix? It's M times N. So the space usage is the same as the time usage. But we can actually do better for space. Right? No, we did talk about space because there was something where, oh, yeah, multiplication. Remember when we started off and I showed you that instead of like working out the multiplication to use quadratic time in quadratic space, you could use quadratic time in linear space. We'll get there. Something like that. Yes, this is definitely dynamic programming. So yes, you can solve the minimum sum subarray with dynamic programming. This is something. There's a reason we're spending all this time on this. Okay, so now the thing is, what if you filled in the top row, and then you know this one, so you fill in the second row. Well, once you've filled in the second row, you don't need the top row anymore. If you just want the cost, you might need the top row if you're keeping track of these blue arrows and you actually want to recover the path. But if you just want the cost, then once you've filled in the top row, you filled in the second row. Once you filled in the second row, you can throw the top row away. Then you fill in the third row, then you can throw the second row away. So actually, you only need a 1 by n matrix, well, two 1 by n matrices. So yeah, you can actually do this in, it takes O of mn time, but it takes O of n space. Well, actually, I mean, you could do the same thing if m is, in this case, m is smaller than n. So you could do it column by column instead. And so you could use it, since if m is smaller than n, then you can use O of m space. But that doesn't give you the the path. It just gives you the cost. And then maybe you can work out the, okay, let's not go there. I would have to actually check something. Whereas last night, instead of checking stuff, I was drawing this matrix. So, are people following so far? They could solve this problem, right? They could come up with this program to work out this cost, and they could do it in quadratic time, and if they needed to, they could work out this cost in linear space. Do people get that? Yes, makes sense, good. Okay, now I'm going to tell you, while we're still working in this very easy, simple, I'm going to erase these blue arrows because they're confusing. Okay. The matrix path game. While we're still just thinking about this easy problem, I'm going to teach you a trick to speed things up. Not always. Okay, this doesn't work always, but it works a lot, and it's worth knowing. It's called banded dynamic programming. So, the idea behind banded dynamic programming is, what if I ask you to get from here to here, and all you have, and remember it costs, crossing a red edge is banded, yes, banded. I think, actually, I'm not sure I've ever seen it. Banded, not banded. No, it's like, yeah, this would be more like a video game. There could be a bandit wandering around in the matrix. No, banded. So I think, other people have other names, maybe have other names for this, but this is, I think, what I've heard it called. Okay, so the idea is, suppose I ask you to go from here to here. You have to pay $1 to cross a black edge. Crossing a red edge is free. But all you have in your pocket is like $5, $6, okay? Or whatever it costs to get here. Let's say 8. Okay, all you have is $8. Okay, so you have a budget of $8. Then, can you get here? No, you can't get here. Could you get here? I don't think so. Okay, because notice that if I'm gonna have to erase this again. Okay, so memorize this. It's about to disappear. So the idea is, if you have a limited budget, you have a really small budget, so you want to get, you have only $8. So you don't care if the cost to get down here is like 15, you can't make it. So you just want to figure out if you can get from this corner to this corner on your budget of $8. Now, the observation is you can't get very far off the diagonal with only $8. Okay? Because think of the cost to get to Aij. If j is much bigger than I, right? So whenever you follow a red edge, so the row increments and the column increments. The only way you can get either the row much bigger than the column, well, okay, let's say the column is much bigger than the row, is to take steps to the right. If you take steps diagonally, it doesn't increase the difference between I and j. So the only way you can get a big gap between I and j is if j is much bigger, you took steps to the right, and that was expensive because each of those cost you $1. And if I is much bigger than j, then you had to take steps down, and those are expensive. So you can't get very far off the diagonal with only $8. In particular, to get to Aij, costs at least absolute value of I minus j. Okay? Do people get that? Okay. So, now actually 8 is not going to really do a lot for us here. But all you're going to see, if your, so if this is 0, 1, 2, 3, so these are actually, these are the costs, but these are also the row numbers. If this is A09, the difference is bigger than 8. You can't get there with $8. Okay? You don't have to work out this cell. You don't have to work out this cell. You don't have to work out this cell. You can get here. Okay? you can't get to this cell or this cell or this cell or this cell or anything above that. So it's called banded dynamic programming because if it's 8, actually I'm going to do this in green. If I give you $8, you know you don't care about anything up here because the cost is above 8. And you don't care about anything below here because the cost is above 8. So now this didn't help you very much in this particular case, but you can see that you have a band. This is where the name comes from, a band that follows the diagonal. So you don't have to work this out. So if instead of if I had said 4 instead of 8, the band would be much narrower and you'd only be working out the stuff in the band. So that actually really helps. So that in general, if somebody says, where did my black go? If somebody says, okay, I want you to figure out the cost of going from here to here on a budget of K, then what it actually takes you, you can do the band is going to be of width about like K. I mean, it's like K up and K this way, right? So it's actually going to be, if you have a budget of K, you can work out the cost in ONK time. Okay? Because you just figure out the values in the band. If you ever think about going over here, you'd be like, nope, don't need to. I already know it's too expensive. So if you know that the path is going to be pretty cheap, then it's actually quite fast to work out the path. Okay, so that's called banded dynamic programming. And if I start thinking that principles of programming languages are, might be catching up, then I might like put that on an assignment or something. But it's actually a trick that it really, really helps because, and it really helps in real life as well. Because quadratic, if you're dealing with something, billions of string, like something billions, each dimensional matrix is billions, and then, so this is, okay. We're going to get to an example where if you try to do something and it's quadratic, you're going to spend more time than the rest of the life of the universe. No, maybe not. It's not that. It could be. Yeah. 3 billion times 3 billion. I don't know. Okay, so people now are totally sick of the matrix path game, right? But you could work out this algorithm, you could do it in linear space, you can do banded dynamic programming. Now we want to see something, I'm just waiting for the timer to run out. Now we want to see something serious. Okay, we want to see why people get really excited about dynamic programming is, well, one of the classic examples, and that you will find out later if you take the bioinformatics courses, is genome alignment. Or a thing like you have a snippet of DNA, a read or something like that, and you want to find out where it matches most closely in a genome, in a reference genome. Okay. So I'm going to get rid of this. You remember banded dynamic programming? So, alignment is if, for example, I have two DNA strings, such as gata, cat, and agata, katka. Okay, and I want to know how these things might align. Okay, so an alignment of two DNA strings is sort of how you would match the characters up. So well, let's do one line. Okay.